All right, welcome back to the counting slides. Let's go and finish those up. So last time we were talking about counting multisets, so sets where you can have a bunch of duplicates, and that's where we stopped. So let us start with some questions for you, just to remember we learned everything. So this first question is not about multisets though, so before that. This one is a bit different, a bit simpler, I think. So see if you can come up with an expression for, or the actual number, for how many different strings you can find of length 12, so strings of length 12, and those strings must have exactly 4 B's somewhere in them, no more, no less, and the strings are chosen over the alphabet A, B, C, D, we say. So when you're making your strings, you can only use the letters A, B, C, D. You need 12 of those characters, and you can choose any of those for any spot as long as you have exactly 4 B's, okay? So see if you can get that to work and come up with an expression for how many strings you need, how many strings there are. So, assuming you tried that, here's the idea. It's like you're picking what's going where and you're trying all the possibilities, right? So you have 12 characters you need to pick, right? And they have indices like 1 through 12, I guess. These are all the characters you need to pick, and they need all these little boxes need to be filled with A, B, C, or D, right? The trick is, because you must have exactly 4 B's, up front, you better pick where those 4 B's are going, right? Maybe we pick these 4 boxes for the B's. And so there's a question of how many different ways are there to pick 4 indices for those B's to live in this length 12 string? And the answer is, because the order of like how do I choose the 3, 4, 11, and 12? Because that order doesn't matter. It's 12 choose 4. Okay, so we're using combinations here. That's how you pick where you're putting those B's. And then notice that the rest is easy. You have 12 minus 4, so 8 places left to fill, 8 boxes left to fill with characters, and you're not allowed to use B anymore, right? So you can only use A, C, or D. You have 3 options, 1, 2, 3 characters, 3 options for each index, and you have 8 indices left to fill, and so that's 3 to the 8. Those are all the different ways you could fill the rest of the boxes with any of those 3 characters. You have 3 options for each box and 8 of them to fill. Does that make sense? So it's 3 because you can only choose from A, C, and D. B's not allowed. We picked all the B's here. Okay? So that, I'll put a box around it, is our answer. Please yell at me if you have any questions about it. So now let's go to an example that I do believe involves multisets. So let's say we have a bunch of coins, like a bunch of piles of coins, and we have divided them into 4 piles according to whether they are pennies, nickels, dimes, or quarters. So we have a bunch of different stacks of pennies, nickels, dimes, and quarters sitting on our table. And the first question is, how many ways are there to select 25 coins from those piles? We're not sure which ones we want. You can pick all 25 pennies. You can pick like 5 pennies and 20 nickels. You could pick 1 penny, 1 nickel, 1 dime, and then 22 quarters. So those are all your options, okay? But you can pull multiple quarters. You can pull multiple pennies. So how many ways are there to select just 25 coins in general from those piles, okay? And so this should screen counting multisets, right? Like we're picking puppies. So let's go back to the formula. What do we want? Well, I want so many. Maybe I want 3 pennies, so I make a binary string with 3 ones. And then I want to say that I'm ready to start picking nickels now, so I put a 0. And then maybe I want 4 nickels, and then I put a 0 to say how many dimes I want. This is how you can precisely represent your choice. Maybe I want 1, 2, 3, 4, 5 dimes, and then you put a 0, and you put as many quarters as you want, and it must add up to 25 ones, right? You have 25 ones, that's the number of things you're taking, right? If we go back to this, you're taking n things, and you have how many varieties? 4, okay? 4 varieties again, pennies, nickels, dimes, and quarters. So m is equal to 4, and so if you do the equation, how many ways are there to pick? It's n plus m minus 1 choose m minus 1. So that means we want to, we have 25 plus 4 minus 1 is 28. 28, choose 3. That's the number. That tells you how many different ways there are to select 25 coins in general from those piles, counting multisets. Okay, so that's the first one. And now let's try B. How many ways are there to select 25 coins if at least 5 must be quarters? Okay, at least 5 must be quarters, and so you're kind of forced to pick 5 quarters for sure. And then also remember that we're assuming that all coins of the same type are indistinguishable. Like, it doesn't matter if you pick the shiny quarter first and then the dull quarter second. You could do that in the opposite order. It doesn't matter. Okay, so that should help you. So see if you can come up with an equation for that. So, assuming that all quarters of the same type are indistinguishable, there is just one way to pick 5, right? There's one way to pick 5 quarters. Just grab 5 of them, okay? It doesn't matter which ones. They're all indistinguishable. So that is the trick there. There's only one way to pick 5 quarters. And that seems kind of weird until you think about it for a long time. I promise it will make more sense. Because they're indistinguishable. Doesn't matter which 5 you pick. It's just, I need to grab 5 quarters. Let me do that. There's only one way to do it. Just pick 5 of them. And then, what else needs to happen? Now we have 20 coins left that anything goes for. We can pick 20 coins out of any of these stacks now. Some of them could still be quarters. It's fine. So it's 1 times all the number of ways to select 20, just 20 coins now from the piles. Okay, I hope that makes some sense. Which is now n equals 20, m equals 4, right? So it's 20 plus 4 minus 1 over 4 minus 1 again. So now it's 23, choose 3. That's the number of ways. Because you're forced to grab 5 quarters, and because they're indistinguishable, that makes no difference. There's one way to do that, and then it's the rest that tells you your options. Okay, so 23, choose 3. That's the answer. All right, so now we remember all that. Let's learn some new stuff. Let's talk about inclusion, exclusion. And this is actually something you might have seen before. I think I saw it in like high school where we're talking about Venn diagrams. Let's come back to that. So first of all, notice that when you have 2 sets and they don't overlap, the size of all the things in both the sets union together is each individual size added together. So like if this is S1, it's got a bunch of stuff, and this is S2, it has a bunch of stuff. There is no overlap. Then the union, right, the number of things in the union is just, well, the number of things in S1 plus the number of things in S2. That's easy. The issue arises, though, if they do have overlap. So you can't do this anymore. If S1 is this, and S2 is this, and they have some things in common, you can't just add, because that would overcount. You see that? You'd overcount everything that they share. Can't do that. So here is the secret. Here's how you count the size of union together sets where there may be some things being shared. It's called the principle of inclusion exclusion. Okay? Lets you count the size of a union of sets. So here's the trick. If A and B are 2 sets, then the size of their union is the size of A plus the size of B minus the size of their intersection. Okay? Let me make this make enough sense to us. So A, here's B, and they do overlap a little bit. So let's say that A has 6 things in it. Boop, boop. And then B has, I guess, 5 things in it. And they overlap on 2 of those things. So the size of A union B is the size of A plus the size of B. Notice that that's going to count these and these, but it's going to count these twice, the stuff in the middle twice. We only wanted to count them once. So we subtract the size of the stuff in the middle. And so we just end up counting them only once now. Okay? So it's 6 plus 5, that's 11. Minus 2 is correct, right? That's just 9. That is correct. 6, 7, 8, 9. It worked. We don't want to double count, so we get rid of that double counting with this subtraction. Okay? So that's inclusion, exclusion, just with sets now. And you can do this for multiple sets. You don't have to do it for just two. There's a way to make it work for a bunch of sets. So let's say that you have A union B union C, and you want to figure out the size of that. That's when it gets a bit weird, because like A and B might share some things, A and C, they might share some things, like there's some overlap. Like here, in the middle among all three, and then among just two in different ways. So it definitely gets uglier when you have more sets. So that size is A plus B plus C, and then you overcounted some stuff a weird number of times. So you got to get rid of those intersections of two sets, every possible one, you subtract. But then you actually took away the intersections of all three too many times, and so you have to add it back in. So there's a plus now, the size of the intersection of all three of those sets at once. And so I'm not going to waste time trying to teach you the general pattern, but there is a pattern here, and it works for any size set. Definitely take a look at the book for that one. It's a cool idea, but there's a lot there. Okay, so this is as much as I want you to know. Just this two sets example, hopefully you can understand it. Okay, you see why we double count, and that is a good start for now. Okay, so that's inclusion, exclusion. And now I'd like to teach you about something a bit more algorithmic, because this is, of course, computer science. Let's talk about how to generate, like, all the permutations of a bunch of numbers, all the combinations of a bunch of things, okay? And the way that we're going to do it is we're going to generate them in a certain way so that we know we're not skipping anything, okay? We're going to generate all these permutations or combinations in a certain order, and it's going to be lexicographic order, okay? So if you haven't heard this word before, it's just a fancy way of saying dictionary order. So like A comes before B, things like that. But we have more than just letters. We have numbers. We have to like say, okay, % comes before open paren. You have to make these kinds of judgments, and we just use the ASCII table for it. But this is how you use strings, like the string library in C++. It enforces this. Like if you try to compare for less than on strings, this is going to be true, right? ABC is less than BCD because ABC comes before it in the dictionary. Same with ABC and ABD. Like the reason why is well, the A's match, but the B's match also, but the C and D, the C comes before D. Yeah, that's how you do it. Additions of like adding numbers and special characters, it makes it a bit weird, but I think you get the general idea. So we're going to order our stuff in lexicographic order. We're going to pick an ordering, and the algorithms that I'm about to teach you that your book has are generating those permutations and combinations in lexicographic order. Okay, so in your future lab, you will be generating these things. You'll be implementing these algorithms that I'm talking to you about now. Okay, so here are the algorithms from the book. Let's do the permutation generation one first. It is a combination of these two functions, and here I have them in pseudocode. I just stole them straight from your book. So here's the algorithm to generate all the permutations of a bunch of numbers in lexicographic order. So you'll be like gen lex permutations, and you'll give a number n. And the point of this function is it's supposed to generate all the permutations of just the set of all the numbers from 1 to n. 1, 2, 3, all the way to n. So that's what it's going to do. You give me the number n, and I'm going to give you all the permutations of the set containing 1, 2, 3, all the way to n. So it's a set of n things, okay? Now, you might be thinking, like, I want to generate the permutations of a bunch of letters, of a bunch of strings, of a bunch of soda types. What is 1 to n going to do any good for me? Well, the way to get around that, the way to generate all the permutations of something other than numbers, is to just simply assign whatever you want to those numbers. Be like, all right, I'm generating all the permutations of every character in the alphabet, so I'll just assign A to 1, B to 2, Y to n minus 1, and Z to n, right? That's all that needs to happen. And then I'll generate all these permutations and just replace, because it's going to output a permutation of these numbers, I'll just replace that with my characters, with those things that I really wanted to make the permutations of. Okay? So this is more general than you think it is. That's what I'm trying to say. And now we can get into the actual algorithm. So here's how it works. This function makes a lot of sense. It is going to generate every permutation in lexicographic order, so it's going to start with the smallest one. That is all the numbers in order, right? AB all the way to YZ. That is the smallest possible string of that size. Yeah, that should make sense. And so it's going to output that. That's a valid permutation. And then it's going to repeatedly use next perm. So give it that permutation to get the next one out of it, using it, output that, and just repeatedly output and generate the next permutation until the next permutation you outputted it was the very last one. That was like ZYX all the way down to BA, right? ZYX down to BA. That's the biggest string in this alphabet, right? In this dictionary. And so that's the last permutation in order. I hope that makes sense. So that's where we want to stop. So we generate it, we output it, and then because we just outputted it, we're done. There's nothing after it. There's no next permutation after the last one, so we stop. Okay? So this function should make a whole lot of sense. That's easy. It's just throwing off its work to next perm, but it is next perm that's the hard one. It takes the current permutation and it generates the next one in lexicographic order, and we need to talk about it. Okay? So let me, instead of just telling you all these words, which get a bit fuzzy, let me give you an example of doing it in order. And oops, it looks like I forgot to take some stuff out of the slide, sorry. So let me show you how next perm works for n equals 5. So we're generating all the permutations of all the numbers from 1 to 5. All right, so the very first thing we do is we make our first permutation. That is all the numbers in order. So p starts out being 1, 2, 3, 4, and 5. And then we give that off to, like, we output that permutation, and then we give it to next perm to generate the next one. So it's taking those elements of that permutation, it's generating the next one. Okay? So the first thing next perm does is it finds an index. Let k be the largest index such that p of k is less than p of k plus 1. So, oops. Think of these as indices, like 0, 1, 2, 3, 4. It finds the largest index, calls it k, such that p of k is less than p of k plus 1. So it is smaller than its next thing. So what are all the places where if k was this, is it smaller than its next element? Yes. If k was 1, is it smaller than index 2? Yes. So on and so forth. We want the largest k, though. So this is the largest k. This is our pk. Because p of k plus 1 is this one, and it's less than. Okay, p of k is less than p of k plus 1. I hope that makes sense. So that's what it finds first, and that is going to be used to generate the next permutation. Okay? So if you didn't find one, if it was always the case that the next element in the permutation immediately after something was bigger than the one that came before it, that means we're in the last possible spot. We are at the last permutation. Everybody's bigger than the ones that come after them. Does that make sense? So that means we're done. That was the last permutation, if we ever got there. Otherwise, we need to find another index. Let j be the largest index such that p of j is greater than p of k. So we're finding the biggest index that holds a bigger value, okay? We find all the bigger values compared to pk, and we find the biggest index for that one, okay? So where are all the bigger values? Bigger than 4? Well, it's just this one. And we find the biggest index that is bigger than 4, and yeah, it's totally here. This is pj now. Okay, so j is this index 4. I hope that makes sense. And so now we have pk and pj, and here's what happens. We swap pj and pk, so that gives us this. Boop. 1, 2, 3, 5, 4. And then the final step is reverse all the order of all the things that come after p of k. So p of k plus 1 all the way to p of n. We reverse those things, and that is our final permutation. So here we go. So everything after this, so at index k plus 1 onwards, so it's this one. From there onwards, reverse everything. Well, there's just one element. There's nothing to reverse. So this is, in fact, the next in lexicographic order. It's the next permutation after this one. And I think if you scratch your head long enough, it makes sense, right? You can't get a smaller permutation other than this one that comes after this. Okay? So that's the next permutation in order, in lexicographic order. And then we can give this, we can output it, we can give it itself to next perms. And let's see what happens if we call next perm on that one. What's the one that comes after the second permutation? So again, we need to find the largest index such that p of k is less than p of k plus 1. And so can't do this one, but we can do this one. 3 is less than 5, so this can be our p of k. Boop. P of k. And then after that, we need to go and find the largest index such that P of j is greater than P of k. So what are all the things greater than 3? We have 4 and 5, but we want the greatest index, not the greatest value. So what's the biggest index among all these things bigger than 3? It's this one. This is the bigger index. So this will be our Pj. Okay? That's going to be our Pj. And then we swap them. So that's going to involve us moving these around. We're going to swap these two out. Boop and boop. Let me do this over here on the side, I guess. So we swap these two. And our intermediate step involves making this permutation. 1, 2, 4, 5, 3. Okay? And then, what needs to happen after that? We need to reverse the order of all the pk plus 1s all the way to pn. Okay? So this is, pk is still here. It's just an index. So everything after pk plus 1 onwards, are these guys. And then we reverse them. So we create this permutation. 1, 2, 4, 3, 5. Okay? And that is the one we give back. That is the next permutation after this one. Okay? So that's the final one that we give back, which is going to be, bam, we put it here. 1, 2, 4, 3, 5. That's the next permutation in order. Okay? So we output it, we can give that to next perm, so on and so forth, but that's the strategy. Okay? I hope that makes a bit more sense now that I've done it, and not just read you in English all these long words. That's how next perm works. It takes a current permutation, finds the next one. And eventually, it will cycle through all of them in lexicographic order, find you every single one. Okay? So definitely try this yourself now. So here's a permutation. Consider this permutation, like we're at this one, of the set of all the numbers from 1 to 7. What is the next largest permutation? Okay? So use this algorithm, use next perm, pause the video here, write down the permutation, and use it on this one. 5, 4, 7, 6, 3, 2, 1. Okay? So give that a try. So, step 1, find the biggest index, k, such that P of k is less than P of k plus 1. So, that won't work. This could work. That won't work. That won't work. That won't work. Oh man, that won't work either. So it looks like this is the only option for our P of k. There's our P of k. It's less than 7. That's the only one that works, actually. That's our P of k. And, okay, then we need to go off and find j. Oops. Let j be the largest index such that P of j is greater than P of k. So what are all the things bigger than 4? Well, we have this one, this one, this one, and that's it. So we want the biggest index, and so it's the one holding 6. It's the one farther towards the right. So this will be our P of j. Yeah? And then we swap them, right? We got to swap P of j. Oops, I keep going to that one, sorry. Swap P of j and P of k. So that gives us this intermediate step, 5, and then we swap 6 and 4. So it's 6, 7, 4, 3, 2, 1. And then, this is still k, this is still index k, right? We take everything to the right of it, these guys, P of k plus 1 onwards to P of n to the end, and we reverse that order, and that's the answer. So the final answer is 5, 6, and then 1, 2, 3, 4, 7. You see how that's like, the subpart is in order from smaller to largest? That's making the next bigger permutation, right? Because this is as small as you can make this side. And use up all the correct numbers. Let me write this a bit cleaner. 3, 4, 7. So that's the correct next permutation. Okay, did you get that one? So that is the kind of thing you will be doing in code. So think about how you might discover these P of Ks and P of Js, yeah? So that's how you generate all the permutations. And the next thing that I want to teach you is how to generate all the combinations, okay? So that's where order doesn't matter, and so we're generating sets instead of ordered pairs, I guess. So how do you generate all the combinations in lexicographic order? And now this is where the book syntax gets a bit weird. Like, this is supposed to represent a set where the order doesn't matter, but pretend that the order does matter, because we're going to output a set in order, and that's going to allow us to eventually generate all the sets in order, okay? So here's how you do it. algorithm to generate all combinations in lexicographic order. You're going to call genlex subsets with 2 numbers, and here's what it does. Here's what this function does. It generates all the subsets of size r. It's all the r subsets of, or from, out of the set containing the numbers 1, 2, 3, all the way to n in order. So it's picking out all the different subsets of a certain size, could be size n, could be smaller, from this set. Okay, and again, you can assign characters to numbers, and so this is more general than it looks, but it's going to output all the sets of size r from this set, all the subsets of that size. Okay, so again, it is a function that makes sense. So here's our first lexicographically ordered subset. You just take all the numbers 1, 2, all the way up to r, because that's the biggest thing that we want. Like if we want a size 5 subset, 1 through 5 is the first possible subset. That's the smallest possible one. So we output it, and then we repeatedly generate the next subset, given the one that we have currently. Okay, so we pass along n and our current subset, and we output the next one. And then we repeatedly do that until we outputted the very last one. There's nothing left. This is the very last subset in order. And you consider the things between the braces in order for, I guess, a weird reason for once, because we do care about lexicographic ordering in the output, because that tells us when to stop. Okay? And so this is the biggest possible subset in lexicographic order. Okay? That's the idea. So we don't want to... We want to make sure that we don't like output 1, 2, 3, and then also 3, 2, 1. Those are the same subset. So we keep a special order on this. That's what I'm trying to say here. Okay. So for once, we're caring about the order of the things that we're outputting, even though it's a set. All right. So this is easy. And again, next subset is the hard part. So let's talk about it. All right. So let's pretend that we want to generate all the subsets of all the numbers from all the size 3 subsets of all the numbers from 1 to 5. Okay? That's the idea. So first of all, using this, what is the first subset? It's 1 all the way to r. So it's the very first subset of size 3 of all the numbers from 1 to 5 is 1, 2, 3. That's 1 to r. Yeah? What's the last subset? What's the last one we output? It is n minus r plus 1. That is 5 minus 3 plus 1, so that's 3. Last subset starts with 3, and then it goes increasing all the way to n, so 3, 4, 5. That's the last possible subset that we're going to generate. Okay? We're generating all the subsets of the set from 1 to 5. That's this. 1, 2, 3, 4, 5. We're generating all the subsets of size 3. Okay? This is the first one. This is the last one. Yeah? And we're doing it in lexicographic order so that we don't skip anything, and it makes it for a nice algorithm. So, we're ready now. Okay? So we have our first one. We outputted it. And then we need to find the next one. Using 1, 2, 3. What's the next subset in lexicographic order? It will be following this. Okay? So we need to calculate this. We need to find k. Let k be the largest index, again, such that s of k, where this is a subset. This is our little subset. It's indexed with s sub something. S of 1, s of 2, s of r. We want to find the largest index such that s of k is less than n minus r plus k. So let's calculate that. N minus r plus k. Okay? So that's going to be, for our case, 5 minus 3 plus k. Yeah? And so we got to check. These are our indices. Apparently they start at 1. We have to care about that now. So we want to find, this is index 1, index 2, index 3. We want to find the largest index k such that s of k is less than n minus r plus k. So we check and say, hey, is s of 1, that's this guy, is that less than 5 minus 3 plus 1? Because that's k now. These match, 1 and 1. is S of 2 less than 5 minus 3 plus 2? If so, that's a bigger number. That could be our k. Is S of 3 less than 5 minus 3 plus 3? So this is what? 2, 3, 4, 5? Are any of these true? Is S of 1 less than 3? Yes. Is S of 2 less than 4? Yes. Is S of 3 less than 5? Yes. So they all work. And so we pick the biggest one. What's the biggest k such that S of k is true for this? So it looks like this is going to be our S of k. Okay? That's how it's going to work. And then we're off to the races. What do we do there? So if there is no such k for this, that means we were at the last one, just like the previous algorithm. But if there is one, then we're good. We can keep on doing this. So then we set S of k to be the next one. S of k equals S of k plus 1. So it's going to increment this, okay, from 3 to 4. It makes 1, 2, 4 out of the deal. And then, for every element afterwards, it's going to increment it. Okay? So everything after index k, there is nothing after index k for us. It's going to increment everything. And so there's nothing to increment here. So we don't have to, we can just skip this loop. There's nothing there. And this is our next permutation. Or sorry, our next subset. Excuse me. And so that's what's going to happen. Okay? I hope that made a bit of sense. And so again, we're going to keep playing this game, and I think you can imagine what's going to happen next. It's going to again find this number. S of 3 is still smaller than 5 here, so we can still increment this one. 1, 2, 5 we can make. And then finally we need to do some stuff. What's the next one after this? We have to find the biggest index such that is S of 1 less than 3? Yes. Is S of 2 less than 4? Yes. Is S of 3 less than 5? No. Now the biggest one is this one. That's going to be our k. And this is now our S of k again. And then we're going to increment that, and we make 1, 3, and then everything after it gets incremented from k plus 1 to r. So for all these things that come after it, here onwards, those get incremented in this way. S of j is S of j minus 1 plus 1. Okay? So it's, okay, what is this one? It's the one before it plus 1. It's essentially incrementing the one that came before it, actually. That's a better way to say it. So this makes 1, 3, 4. Okay? That makes 1, 3, 4. And again, the next k can be this one. We increment it to 1, 3, 5. That's the next subset. And then what happens? Then again, it's this one that needs to change. So we're going to increment from 1, 3 to 1, 4. That's going to be our S of k again. We're going to increment it to 4. And then we're going to run our loop. So for everything after it, the next element, j, is the one before it plus 1. So it's going to make 1, 4, 5. Okay, because that's 4 plus 1. 5 is 4 plus 1. And then after that, what's the next subset of size 3? It's going to be, sorry, that's supposed to be a brace. Well, 4 is not less than 4. 5 is not less than 5. But 1 is less than 3, so now we can actually increment the 1. Ooh. We make the 1 a 2. This is now our S of k. Make the 1 a 2, and then everything after it, we run that loop. Oops. Everything after it becomes the thing that was before it plus 1. So what goes here? It's thing before plus 1. It's the 3. And now what goes here? Thing before plus 1. It's 4. And so now in order, it's generating all of these subsets. Okay? And eventually it's going to get to 3, 4, 5. Okay? Hopefully that is making a bit more sense now that I gave you a bunch of examples. That's next subset. Okay? So think about how you might implement that, because you will be. Prepare yourself mentally for it. Okay? This is very, it's not a lot of words, but it gets a bit tedious. There are a lot of details there to remember. Okay? So that is the algorithm. And now we can talk about, I would say, simpler things. Okay, we don't have to think too hard about some of this stuff now because we've learned it before. Binomial coefficients, for example, is something we've learned already in a math class. So let's talk about that. So a binomial is just a number that has two things, right? Bi for binomial. You're adding together two things and you're taking that to a power. That's what a binomial is. So if you take b plus o to the third power, that becomes all this, right? It's, well, you can take 3 b's, or you can take 2 b's and then an o, or a b, an o, and a b, or 1 b and 2 o's, on and on until you've tried every option, right? So it's kind of trying a bunch of permutations, like your FOIL rule is turning into a bunch of permutations. That's pretty cool. But the order of those don't matter, right? 2 b's and an o is still 2 b's and an o, right? Still 2 b's and an o. So there's 3 of those. And you can bring them all together. So there's 3 of those. Isn't that cute? So there's 3 of those. There's 3 b's and 2 o's. There's one way to make o cubed. There's one way to make 3 b's. Yeah? The order doesn't matter, and so we can bring them together like that. So it's kind of like we're turning permutations into just a bunch of subsets. Like these are how many times we're overcounting. Yeah? We're counting the same thing. That's kind of cool. So it's definitely bringing together all the stuff that we've learned before. So the order doesn't matter. That tells us a little bit about subsets, and so we might see some combinations come into play, and you can see that in one of these bullets down here. So these coefficients, this 1, 3, 3, 1, 1, 3, 3, 1, if that's the order, those are special. Those are called binomial coefficients, and you can actually calculate those ahead of time, okay? And also an interesting fact is that they read the same forward and backwards. 1, 3, 3, 1 is 1, 3, 3, 1, no matter what. So that's kind of cool too. So, and these particular coefficients, you can come up with them with this thing called the binomial theorem. And so the binomial theorem says that if you're taking a plus b to the n, it could be anything, and you want to know what's the coefficient in front of a to the k times b to the n minus k, because these all need to add up to n every time, right? This is 3 and 0 o's. This is 2 b's and 1 o. It always adds up to 3, right? So this always adds up to n. What do you want? What is this coefficient? How many times do you see this in some weird arrangement? Well, it happens to be n choose k. All the different ways that you can choose k things out of n things. And that, because it's the same in reverse, means this is equal to n choose n minus k as well, because it's a palindrome, which is really cool. So you can think about this coefficient from k's perspective or n minus k's perspective, and it ends up being the same answer, which is really cool. And the binomial theorem proves that to us. So that's awesome, and that's very helpful for math, right? So where does this all come from? We've definitely done this before. You've seen Pascal's triangle before this, right? But maybe you haven't seen it being done with combinations. So Blaise Pascal invented his triangle, and it's just a chart that tells you how n choose k is related to previous things. Okay, you're trying to calculate all these things. So along the side is always 1, right? 1, 1, 1, 1. How many ways are there to choose 0 things out of a size 4 set? Just 1. This is also 1, 1, 1, 1. How many ways are there to choose 4 things out of a size 4 set? Again, just 1, because you choose everything. That's your only option. And then the cool thing that Pascal noticed is an identity. The number of ways to select a set of k items from a set of n items, that's this guy, n choose k, that's equal to n minus 1 choose k minus 1 plus n minus 1 choose k. Oh, so this is kind of recursive, right? And these n's are getting smaller. You can throw off the problem to somebody else. So this is actually a recursive solution, believe it or not. And this is Pascal's identity, the way that these combinations are generated. Okay, and it's called an identity because we're showing that two things are equal. Like this plus this is equal to this, and that's what happens. So n choose k. It's really equal to n minus 1 choose k minus 1 plus n minus 1 choose k. And if you draw this in diagrammatic form, that means that 2 choose 1 is equal to 1 choose 0 plus 1 choose 1. And that's going to make 2. Same for all these. 3 choose 1 is going to be 2 choose 0 plus 2 choose 1. Well, that's 3. And then same with this. 2 plus 1 is 3. And you can fill this in until the end of time. It goes on forever. And here is our 1, 3, 3, 1. You see it? Isn't that cool? It's always the same. And so that's Pascal's triangle. It tells you those binomial coefficients, and this is how it's related to everything else. Okay? So, let me actually prove this to you. This is a fun little proof. Like, why does this work? Why in the world? Here's how you do it. So here's our theorem. This is the identity, right? N choose k is equal to this stuff involving smaller n's, n minus 1 choose stuff. And here is the proof. So assume that we're trying to count all the k subsets of a set with n things. That's exactly what n choose k means. Count all the k subsets of a set with n things, right? So let's prove that it's equal to this stuff. So I'm going to prove that k subsets of A, which is n choose k, that is equal to these two things, which will end up being these two pieces. Okay? So if you're trying to count all the subsets of size k of a set with n things, here's how you can split it up. Let's say, for sake of example, let's choose k equal to 3 and n equal to 5. So we're trying to find all the size 3 subsets of the set A equals 1, 2, 3, 4, 5. And I claim those k subsets can be split up into this form. You can find all of the length k subsets that contain this last element, A of n, contain the 5, and all the ones that don't contain the 5. Okay? That contain A to the n, and all the length k subsets that don't contain A to the n. And this is A to the n, it's the 5, for example. Okay? You can always split up this question like this. And so here's all the ways that you can make length k subsets, so size 3, that don't contain the 5. So you got your, like, I don't know, 1, 2, 3. You got your, I don't know, 2, 3, 4. You got your 1, 3, 4. These are all subsets that don't contain the 5, and they're size 3. And then you have all the subsets that are size 3 that do contain the 5. So you got your, I don't know, 1, 2, 5, 2, 4, 5. There are a bunch of options there too. Plenty of them. But do you see how these two sets are disjoint? Like, all these have a 5 in them. All these don't. So these are all separate. These are all disjoint. And so, but together, right, they sum to be all of the different ways that you can make subsets of size k from this set A. Yeah? You can break it down into all the subsets that contain A to the n and all the subsets that don't. And if you believe that, and believe that it's disjoint, we can use the sum rule and just add them together and get the full size. So now, watch these break down. How do you count all the size k subsets of A that contain A, and you know that the 5's there? Well, that's a smaller problem. Because now, because I know that there's a 5 in all of these subsets, there's one less thing to pick out. There's one less thing to choose. Now, I need to choose k minus 1 things, because I know I'm already putting a 5 in this set, and the order doesn't matter. And so I need to choose n minus 1 more things, so 2 more things for each subset. And I have k minus 1 things to choose now, because I already know that the 5 is in there. Does that make sense? That's how you break it down there, and that's the first piece of the puzzle. Then, what's that? Added to all the k subsets of A that don't contain A to the n. That's just, well, if I know I don't contain A to the n, now I'm choosing from one less thing, right? I'm choosing from 1 to 4 instead of from 1 to 5. I have n minus 1 things to choose from again, but I'm still picking k things out of them, right? There's, I haven't made any choices yet. There's still k things to choose from. And so, if you followed all that, it just breaks down, and that's the identity. Isn't that cool? So that's why this works. That gives us the triangle. Like, that's how you prove that this triangle exists and works out. And so I hope that was fun. That is the idea. That's Pascal's identity. And so you can use that to prove cool stuff, to find those coefficients. And that is what I want you to get some practice with right now. So let's try this first one. Let's say that this is our binomial. It's 3x minus 4y to the 8th. And I want you to find the coefficient in front of x to the 5th times y cubed. That's there because 5 plus 3 is 8. That has to be one of the terms of these. There might be a bunch of them. How many x to the 5y cubes are there when you expand this? Okay, so let's follow our theorem. Or, I guess, yeah, our binomial theorem. So the binomial coefficient of a to the k b to the n minus k in this bigger expression is n choose k. Okay? So, for example, our A is a is equal to 3x. Our b is equal to minus 4y. Do we see that? Minus 4y. Yeah? And we want to figure out the coefficient of x to the 5th times y cubed, so we have to have 3a cubed, right, and b to the, or sorry, a to the 5th and b to the 3rd, if we're going to end up with 3 of these y's and 5 of these x's, right? So that's what's happening there. And then let's use our binomial theorem now. So ak be the n minus k. So let's say that k is then, it's the first thing. Let's say that k is then 5. Let's say that k is 5. Yeah? And then finally, n was 8. And so we have n choose k as our answer. But that is not the end of the story. So we are going to end up with 8 choose 5, but we're not yet done, right? So we have this term. We know that it exists. X to the 5th times y cubed. And then, if we had x to the 5th, like, how many times do we have this? We notice that we have it 8 choose 5 times, right? We must have it this way, because the binomial theorem tells us that we have it this way. But we are not yet done because this isn't the final answer. If we ended up with 5 x's and 3 y's, we also took these coefficients, the 3 and the negative 4, along for a ride too. So how many 3's must there have been in this answer? Well, it's 3 that was associated with the x. We have 5 of those, right? It's to the 5th. And then how many y's did we have? We had that cubed, so that means the negative 4 also got cubed. You see that? So this is in fact the coefficient in front of x to the 5th times y cubed. Does that make sense? Remember the extra stuff, not just the variables. Those also have to come along for the ride. If it was x to the 5th, that means the 3 also got to the 5th power. Yeah? That's the secret. So those are all there, and then this is how many times you had all those. 8 choose 5 times. Okay? That's one way to do it. And try to find this one now. X to the 6th, y to the 1th power, or the first power, in this binomial. Okay. So, we have x to the 6th, y to the 1, and because we have that, how many times do we have this? We have it, well, it's going to be 7, choose, and that's just the first one. You can also do this one as well. 7 choose 6 times, we have an x to the 6 times y to the first term. And then we also have those coefficients that come along for the ride. So it's because I have x to the 6th and the negative 2 is attached to x, I have 6 negative 2's as well, right? Because I had y to the first power and I had negative 5 attached to y, I also have negative 5 to the first power. You see that? So that's going to be the coefficient in front. Like these always come along for the ride with x to the 6 times y to the 1. And this is how many times they are repeated in weird random orders, right? Like our bobs and OBBs and things. So that is the coefficient, and that's how you find it. Any questions about that? Please yell at me. So that is all those cool identities, and then I have one last main topic for us for these slides. So let's talk about what's called the Pigeonhole Principle, which is kind of cute. And this is actually a very, very simple idea, but it becomes quite powerful. So it's very simple to state, and it's very obvious, in fact. So this is the Pigeonhole Principle. Let's say, I don't know, you're a pigeon farmer. If you have n plus 1 pigeons, and you know that they are sitting in n boxes, you only made n boxes. So I don't know, let's say that n is 6. 1, 2, 3, 4, 5. I don't know, let's say n is 7. Who cares? 1, 2, 3, 4, 5, 6, 7. And you have 8 pigeons, and you know they're all sitting in these 7 boxes. Then there must be at least one box with more than 1 pigeon in it. That's all. It's very obvious, right? 6, 7. If there's 8 pigeons, there better be one in multiple boxes, right? There better be 2 in one box at least. Okay? It's very, very simple. And we can prove this by contradiction very quickly, right? We can be like, okay, assume, proof, assume by contradiction. Well, assume that that is not the case. Assume that each box has less than or equal to 1 pigeon in it. then the total number of pigeons must be less than or equal to, well, that one pigeon in each of the n boxes, which is n, right? But there are n plus 1 pigeons. And that's a contradiction. Yeah. So that immediately proves that there must have been one box with at least more than one pigeon in it. Okay? And so that's the pigeonhole principle, very simple. And formally, it's usually talked about functions and domain and codomain sizes. So it's like saying like this: if this is a function and here's your domain and here's your codomain, the domain has 4 elements, the codomain has 3 elements. Well, that's forcing the function to pick things, right? You are forced to overlap on at least one of those inputs. The function must overlap on one of the inputs. Like, it takes these two things to the same thing. That's essentially the pigeonhole principle in math. Okay? And this is going to let us prove some cool stuff, in fact. So that's the pigeonhole principle. Here's some examples. So first example, let's say that we have socks in a drawer. Okay, we have 3 different kinds of socks. So we have S1, we have S1, S2, and S3. Those are our different kinds of socks in a drawer, and they're just all strewn about. Like, we have a bunch of S1s, we have a bunch of S2s, we have a bunch of S3s. Those are all our socks in a drawer, and we are crazy, and so we don't put them in pairs. Like, we just have individual socks sitting in our drawer right now. And using the pigeonhole principle, we can prove that in the worst case, you have to take out 4 socks until you find a matching pair, right? Because in the worst case, the first pair you pick is like S1, the second pair you pick is S2, you still don't have a match. The second, the third sock that you pick out is S3, still not a matching pair. And then you already have one of each now. In the worst case, you have to draw one more pair, and then you finally have a match to one of the ones you drew before, okay? And so that is the worst case, and that's the pigeonhole principle. 3 kinds of socks, so you need 4 if you want 2 of them, right? You want to guarantee you have 2 of them. And with that in mind, you can use the pigeonhole principle to prove some really interesting things, like this one. This is the craziest example that is actually true. I promise you that this is true. It makes no sense why, or it seems illogical, but it is exactly true. Okay? So there are 3 non-bald people in Fresno, so 3 people with hair in Fresno, that have the exact same number of hairs on their head. There must be 3 people in Fresno with the exact same number of hairs on their head. Let me prove that to you. So, the number of hairs on someone's head is bounded above by 200,000, let's say. So people have at most 200,000 strands of hair on their head. And Fresno has a population of greater than 500,000. And so in the worst case, following this pattern, like, okay, person 1 has 1 strand of hair, person 2 has 2 strands of hair, person 3 has 3 strands of hair. For the first 200,000 people that you pick out of Fresno, maybe they all have different amounts of hair. But then, for the 200,001th person, and first person, they overlap with somebody, okay? And again, you can play the game where, okay, they have the minimum amount of overlap. And so for 400,000 people, like, you have that much overlapping. And then you have more than that. So like for the 400,001st person, if you try and spread this out as much as possible among all different bins of hair sizes, you're forced to overlap for the 400,001st person. And then you end up like this. So there will be a case where you have some number of hairs where 3 people at a minimum, have the same number of hairs on their head. Okay? It's a weird thing to say, but it must be true. And this is true because if you try to spread it out as much as possible, you give everybody else, like, everybody has a different amount of hair, you try and put 500,000 people in 200,000 bins. Okay? And this is true because when you take this division, it's greater than 2, right? It's greater than 2, so that means there must be at least one case where there are 3. Does that make sense? There has to be some overlap. Think of all these things as pigeons trying to sit in holes, okay? And so technically the way that you get up this answer is like, okay, in the worst case, I'm trying to put 500,000 people spread them out as much as possible within 200,000 bins for hair sizes, hair amounts, I guess. And then you take the ceiling of that, because if there's anything left over, you do have some overlap. Okay, so that's 3. So that's why that comes up. And that is the craziest example, I think, but it must be true. We can't figure out who, but it must be true. Okay, let's have some more examples now. A lot of examples come from like playing cards, so you can pick 5 cards from a deck, for example. Then you must have at least 2 with the same suit, right? I forget all the different suits, right? It's like, in the worst case, if you're picking 5 cards, the first one is clubs, then the next one is spades, then the next one is hearts, then the next one is diamonds, right? Those are all the 4 possibilities. And then for the 5th one, you're forced to choose one that came before, right? Then there must be some overlap. Finally, we have something in common with one that came before. But you got to choose 4 first, in the worst case, to have 1 left over, and then you have overlap. There might be more overlap, but in the worst case, at least 2, right? You have to pick 5, and at least 2 will have that same suit. Okay? Last example, pick 10 arbitrary 2-digit numbers. And this is also a cool one. So pick 10 2-digit numbers. I don't care what you pick. Like pick 15 and 21 and 33 and 87. Just pick 10 of them. Arbitrary 2-digit numbers. There are, among those 10 2-digit numbers, there are 2 subsets of them that have the same sum, which is crazy. Crazy to think about. There are some subsets that have the same sum. So maybe it's like you pick some of these, and then maybe some of these, you add them together. They have the same sum. It's guaranteed. Let me show that to you. So the number of possible subsets of 2-digit numbers is 2 to the 10, right? 2 numbers, 2 to the 10 means you either have something or you don't have something. You have those options 10 times, so that's 1024. That's the number of possible subsets of 2-digit numbers. And then the set of possible sums is, well, how many? How many sums could you have? Well, of 2-digit numbers, of 10 of them, right? In the worst case, you have 0. You pick your arbitrary 10 numbers were 0 10 times. That's the minimum number. The maximum number that you could have picked was, well, they're 2 digits, so you can pick 99 10 times. That's the biggest number, right? That gives you 990. So the set of possible sums is 0 all the way to 990. And, oh man, what do you think? There are more subsets than sums, right? So there is going to be some overlap. Isn't that cool? There is forced to be overlap then on the set of sums. There must be 2 subsets that have an equal sum because of the Pigeonhole Principle, which is super neat, and that is the reason why. So I think we are running out of time, so let's not try and code this up, but ask me about it in office hours if you'd like. But that is another example. All right, and now I have some questions for you, and that'll be it. So try these questions about the Pigeonhole Principle, and then we'll go over them. So the first question is, how many people must you select? So what's the size of the group you need to make sure that there are at least 20 people in that group who were born in the same month? Okay? So think about this. So in the worst case, you always got to think about in the worst case, the first 20 people that you pick to be in your, or the first 12 people that you pick to be in your group are all born in different months, right? 4, 8, 12. They were all born in different months and there is no overlap. So that's the worst case. Stuff like that happens for the rest of time. So you pick another 12 people and they have the minimum overlap. The minimum overlap again. So now you've picked 24 people and at most there are only 2 people who share the same birth month. And you can keep playing this game forever and ever and ever. So the minimum amount, right? You could pick 19 times 12 people in the worst case, right? And still not have 20 people who are born in the same month. They were all, like you have 19 groups of people who are all born in January. Or you have 12 groups of people. 19 were born in January, 19 were born in February, all the way to December. And you're still stuck. Nobody has, you haven't found 20 people to overlap yet. And so you need just one more, right? You need just one more to bring you over the edge. Okay, and that'll force this to happen because you are, like, if you try to spread them out as much as possible, like you're trying to find an n such that when you divide by 12 and you take the ceiling, that better be greater than or equal to 20. You want to find the smallest n that makes this work, okay? Because that will give you, if you try to spread them out as much as possible among all those 12 places, that is going to be the size you need to ensure that you have at least 20 people born in the same month. Because if you do 19 times 12, you pick that many people, you divide that by 12, that's just 19 still, right? But if you do one more and you divide that by 12 and take the ceiling, oh, that's 19 point something, and that gives you 20, okay? Because that's going to be your overlap. That's going to be the minimum amount of people that you need to make sure that you got 20 who are born in the same month, because you might have the worst case where everybody's spread out as much as possible, okay? And so it comes back down to that ceiling kind of example, okay? That's what's going to give you that size, okay? So that will be the answer there. So you need 19 times 12 plus 1 people to ensure, without a doubt, it must be the case. Then, only then, do you have 20 people who are born in the same month. Try this next one. At least how many people in a group of 50 were born in July? So that's a specific month. And assuming you thought about that for a while, this is actually a trick question. There is no answer to this question. Did you come up with that? Did you figure that out? There is no answer. Why not? I can pick a group of an arbitrary size. Like, it's not guaranteed that that group was having anybody who was born in July. I can pick 50 people who were all born in January. Can't I? You have no guarantees in this way, okay? So that is a trick question. There is no answer. Pat yourself on the back if you figured that out. All right, this last one does have an answer. So the population of California is about 40 million, and assuming that, at least, how many people have the same 3 initials? Let's assume that everybody in the state has 3 initials, just to make this easier on us. So assume that everyone has a middle name or some other name that makes your total names add up to 3, okay? So how does this work? At least how many people have the same 3 initials? Well, how many options do you have for initials, first of all? You have 26 characters in the alphabet, and you have 3 of them to make an initial, right? Those are your 3 initials, 26 to the 3rd power. That's how many options of initials we have. And we have 40 million people. In the worst case, they are spread out as much as possible among those 26 to the 3rd initials. And then, if we take the ceiling of that, that is the minimum amount of people that have the same 3 initials using the Pigeonhole Principle, okay? Even if they're spread out as much as possible, and you put everybody into as many different groups as you can with the minimum amount of overlap, you are forced to at least have a case where you have this much overlap. Okay? And give everybody as many different initials as you can. But there will be some overlap, and this is what that is calculating. Okay? The minimum overlap. And feel free to look that up on your own. So that is the final answer. That is the slides on counting. Now we are good at counting, in case we weren't before. So that's these slides, and now I'm ready to introduce your next lab. So that's going to be lab 6, your very last lab in the class. It's about those generation algorithms that we talked about today. So I'll go and release that, and then we'll come back and talk about some new stuff, to talk about probability. So I'll see you in one of those videos.